this, and this. Okay, so guys, here's what we're up to today. We are going to talk first about something called Dalton's law of partial pressures. And once we've sort of wrapped our brains around this idea of partial pressures, and guys, I'm going to tell you right now, it's really pretty simple. But once we have a functional understanding of Dalton's law of partial pressures, we're going to talk a little bit about why this is counterintuitive, just like things like Avogadro's principle. Remember that says same temperature, same pressure, same volume, same number of molecules, which is counterintuitive because we would think that big molecules would take fewer than small molecules to fill a space. So we're starting to get comfortable with this idea that gases don't behave the way we think they necessarily would. Well, guys, we're going to talk a little bit about that relative to gas mixtures today. We're going to take those mental models that we've started to develop. We're going to apply our mental models to gas pressures. Then, guys, we're going to study mixtures of gases. We're going to do this mathematically. We'll be solving a couple problems. One of them is exactly like, well, not exactly, but a lot like question number 61 in the homework, but you'll be able to go back and do 61. And then, guys, we're going to pull one of the equations out of the AP equation sheet, talk about what that means, and then call it a day. Shall we? Okay, you ready? So guys, let's start with Dalton's law of partial pressures, and I'm just going to lay it out there for you. Guys, this is it. It really is this simple. Dalton's law of partial pressure says this. It says the total pressure of a mixture of gases is equal to the sum of the pressures that each would exert if it's all by itself. And guys, your natural response to this, if you understand what it means, should be, duh. Except for if you really understand what it means, you might be thinking, that doesn't seem quite right. But then if you start thinking about what you know about the actual behavior of gases, you should come back to, oh, okay, I see why that's true. So guys, what I'd like to do is I'd like to take you through that entire mental process of, duh, wait a minute, oh, okay. You see what I'm saying? Okay, so guys, let's talk about duh first. Ready? So we're going to jump over here because this is what it takes for me to actually be able to move these things. And guys, what I have done is I've represented two different gases, one in blue, one in red. And you'll notice, we can count because counting will be important in a minute. There are 10 molecules of blue and there are 5 molecules of red, meaning that in fact there's twice as much blue as red. So guys, what does Pivner tell us? The pressure of these gases will be relative to each other. The blue will be larger, but let's talk more specifically. Yeah, so let's talk, oh look, I'm even going to color coordinate Pivner and Pivnert. So guys, here's the question that I want to ask you. How does the pressure of this dude compare to the pressure of this dude? So guys, in order to figure that out, let's talk about our other variables. So first of all, volume. What do you know about the volume of blue compared to the volume of red? They're the same, so those cancel out. What do you know about the temperature of blue compared to red? They're in the same room, or at least on the same screen. So they're the same. R is obviously the same because it's a constant. So now what about the number of moles, the number of particles? What is true of the number of particles of blue compared to red? Twice as much. So what then will the pressure be? Twice as high. Guys, that is an important statement that we're going to quantify mathematically in a minute. But guys, you got to fundamentally understand that there's twice as much blue as red, and all things being equal, those things being volume and temperature, guys, the pressure of blue will be twice that as red. So now let's give it numbers. So let's say, and let me clean up this mess. Let's say that blue has a pressure, let's just use a nice easy number, and red then of course would have a pressure of 1 atmosphere. You guys with me so far? Okay. So now guys, here's what we're going to do. And I've never done it this way before, but I think I'm going to like this better. So I'm going to erase this, and then I'm going to do a little clicking here, and I'll just let you see what I'm doing. So guys, are you convinced of the idea that blue is twice the pressure of red? Is that okay? Okay, so I'm going to clean up my mess. And then guys, what I want to do is this. I'm going to copy this, paste this, move this, ungroup this, and then grab the circle, delete these, and now I'm good. Okay, so guys, with that said, here's what we're now going to do. And let's remind ourselves, what's the pressure of blue? 2 atmospheres, pressure of red, 1 atmosphere. Okay, now guys, what we're going to do is we are going to mix these gases together. Ready? So we are going to take blue gas and we are going to squirt it into that container. What is now the pressure of the gas inside that container? 2 atmospheres. Now we're going to take red gas and we are going to squirt it into the container that already contains blue gas. What is now the pressure inside the container? 3 atmospheres. Duh. Right? Are you guys all at duh? Okay. Now let's move on to, but wait a minute. Because guys, let's do this again. Pull out the blue, pull out the red. So guys, let's put in the blue. What is now the pressure inside the container? 2 atmospheres. Now, is this, actually, you know what? Let me do this. Now guys, let's pull out blue and let's put in red. Now what's the pressure inside the container? 1 atmosphere, right? Now let's put blue back in, 2 atmospheres. But now guys, here's the problem. When we add red, we are adding red to a container that's not empty. And if it is not empty, let me ask you a question. How does the volume of the container now compare to the volume of the container now? It's actually not. It's a little bit smaller because there's stuff in there. Hold on. Wait. You're going step 3 and not everybody's with you. So guys, the idea is this. You take a gas and put it in an empty container. That's 2 atmospheres. That's 1 atmosphere, right? But if we put in blue, now the container is not empty. Its functional volume is a little bit smaller because blue is in there. So now when we put red in there, what is that doing to the volume of red? Making it a little smaller, right? Because there's blue in there. And if blue is already in there, then that means that the volume that red can occupy is a little bit less because there's already something in there. And as a result, the pressure of red should be a little bit higher because we're now putting it in a container that already contains something. You get the idea? So now we're going, wait a minute. But now, guys, let's explain it and bring it full circle so that we can go, okay, it actually does make sense. So now, guys, let's pull this out and let's pull this out and let's talk. So when we put blue in the container, and this is harder to do like that than with the mouse. When we put blue in the container, what's the pressure? 2 atmospheres, right? Now, when we put red in the container, we are now putting it in a container that is not empty. But when we put red in a not empty container, why does its pressure remain 1 atmosphere? Why does its pressure not go up a little bit? Because the blue stuff is there. Go ahead. And why? And that's the answer. The gases don't interact, but why? Guys, no. They're so spread out. So, guys, it's kind of like this. I grew up in Wyoming. I grew up on the edge of a town of 4,000 people in the middle of stinking nowhere in Wyoming. And we had a building boom. In 1985, one person built a house. That's a building boom in Wyoming. And so, guys, all of a sudden, I had a neighbor. I could see him in my binoculars. I'm not kidding, seriously. Oh, it was horrible. The antelope crossing, but guys, seriously, I had a neighbor. And I could see my neighbor in the binoculars, but guess what? It really didn't change my life, did it? Why not? They're so far away. So guys, in theory, my neighbor building a house limited the amount of freedom that I had because now there's somebody over there and there wasn't before. But guys, they're so far away that functionally it doesn't matter. Guys, this is the same way. When we put blue in the container, is there now stuff inside the container? Yeah, but they're so spread out that when you come along and build other houses, when you stick red, and they're not quite lined up, but guys, when you stick red inside of blue, the space between blue is so big that red doesn't even know that blue is there. You get the idea? Guys, that is why Dalton's law of partial pressures works. These things behave as if the other gases aren't there because they're so spread out, they may as well not be there. You get the idea? Go ahead, Austin. But you understand they do, right? Every now and then I would bump into my neighbor at the grocery store. We did, in fact, have a grocery store. We were 100 miles from McDonald's, but we did have a grocery store. And every now and then I would run into him and I go, hey, you're my neighbor, but it didn't really change anything, right? These guys run into each other every now and then. They have to by the law of averages, right? But because it happens so infrequently, it doesn't change their momentum. It doesn't change their pressure. They functionally behave as if the other one's not there. Is that okay? Go ahead. Now, here's where we've got to be careful, and let's talk about this. Guys, what is it about gases that allows this to be true? Given what you learned last time in class, you got to understand this. What is it about gases that allows this to be true? What did you learn last time in class? Gases have low densities, right? So guys, what if the density of the gas were to increase? Well, now we're talking about a building boom in Utah County. If you don't know what I'm talking about, go to Westlake. Guys, they're building houses over there as fast as they possibly can, and you get a neighbor and it changes your life because their house is 4.5 feet away from your house. How do I know that? Because the setback is legally 4 feet, and they're building right up against, actually it's 6 feet, but they're building right up against the setbacks because they're trying to pack as many houses in there as they can. So if gases have higher densities, packing them closer together, and I can even do this. I wonder if I can do it proportionally. Let's go select all and then drag, poop. I was really hoping I could do that for all of them. But guys, let's make this, wait a second, maybe I can. Hold on. Let me hold down shift and see what it does. No. But if I do that, and if I do that, do you see what I'm saying? And we understand this isn't a perfect example. But guys, if this is if this is a higher density gas, and again, how do we make gases more dense? You better know this. Increase the pressure, increase the molecular mass, decrease the temperature. If we then pile these molecules in, if we pile these molecules in here, now their density, because remember the particles actually shouldn't have got smaller, right? Now they're dense enough that they would know that the other particles are there. So the thing that allows this to work is simply the fact that gases are very low density. You get the idea? Okay, so guys, with all of that said then, let's go back and talk about how we describe this reality mathematically. And guys, it's simply written like this. Did I change this to fit? Yeah, I did. So guys, you'll notice that this equation is on your AP equation sheet. Looking at the page 4 side of your AP equation sheet, you'll notice that it gives you this. It is saying that P total is equal to PA plus PB plus PC plus ... meaning it just goes on forever. So guys, functionally, this is Dalton's law of partial pressures. That if you have a mixture of gases, the total pressure of the gas will be the sum of the pressures of the individual components. Were you going to say something? Okay, you guys okay with the idea? Okay, because now, guys, we're going to do some interesting mathematical gymnastics. So, imagine that these gases that are in our mixture are all ideal gases. So guys, if all of these are ideal gases, that means that they all obey Pivnert. Now watch this. So let's solve Pivnert for Pa. So if we solve Pivnert for Pa, we get Nertva. Okay, so Pa is equal to Nertva. So now what we're going to do is we're going to say pressure total is equal to Pa A plus Pa B plus Pa C, but we're going to replace Pa with Nertva. So we end up with this. Pressure total is equal to Nertva 1 plus Nertva 2. Well, this should actually, you know what, hold on. Let me change this. So this would be Nertva... Oh my gosh, more clicking. So this would actually be Nertva A plus Nertva, oh come on baby, Nertva B plus Nertva C. Okay, so guys, now we've got this relationship that says pressure total is equal to the Nertva of gas A, the Nertva of gas B, the Nertva of gas C. Now guys, this is not something you're ever going to have to solve. But if you want to write it down, you will have this satisfying experience of joining me in canceling. Yes. I know. Oh, you know what I'm going to do? I'm going with thick pen. Here we go. So guys, let's do some canceling. Let's do some factoring out, if you will. So guys, looking at the right side of this equation, we can actually cancel R, because that's the same in all three, in all samples in the mixture. Guys, what about the temperature of a gas? If we've got a mixture of gases, what do you know about the temperatures of all the components? They're all the same, so we can factor those out and cancel them. What do you know about the volume of all the components? They're all the same because they're in the same container, so the volumes are all the same. So guys, look at what we're left with. The pressure of a mixture of gases is actually proportional to the number of moles of A, the number of moles of B, the number of moles of C. Hopefully right now you're saying to yourself, wait, that sounds familiar. Because guys, it should sound familiar. Because what we're talking about, ooh, how do I do this? How do I put that? Oh, wait, I think I can do this. Just a moment. There we go. Guys, oh, that's what it was. Hold on. Okay, let me recover from this. So, guys, what we can say then is this. Remember what we did? Let me pull this out of the way. So we said, flipping these around, we said this, right? How did we know that the pressure of blue was twice the pressure of red? Because there's twice as many molecules. Now guys, how do we measure numbers of molecules? What units do we use to measure numbers of molecules? Moles. So what we said is this. Na is twice Nb, right? So Na is 2 times Nb. So if the number of moles of A is twice the number of moles of B, what will the pressure of A be compared to the pressure of B? Twice. And guys, that is exactly what, man, I'm doing a lot of clicking today. Guys, that is exactly what this, oh boy. Come on, baby. That's what this is telling you. I know, right? Guys, this is what this is telling you. That there is a relationship between the number of moles of a component and the pressure of that component. So if we know the number of moles in a mixture, we will also know the relative pressures of the gases in that mixture. Does that make sense? Okay, so guys, let's put a fine point on that and let's say it like this. The pressure that a gas contributes to a mixture is proportional to the number of moles it contributes to the mixture. And that's an important thing to keep track of. So guys, once you're done writing that down, what we're going to do is we are going to take this idea of proportionality, the moles pressure relationships. We're going to take that idea of proportionality and we're going to sort of put that on the proverbial back burner for a minute. And we are going to look at another interesting application of this idea of Dalton's law of partial pressures. And then we're going to come back to the idea of proportionality. I'm kind of wondering if we shouldn't just go solve question 61 rather than the question that I've got for you. You guys want to do that? Okay, so guys, why don't we do that? Let's, I wasn't planning on doing this, but I love just going live without a net because there's nothing more valuable to you than seeing me make mistakes. Seriously. Yeah, no, it's actually because as you see other people work through, you learn to do that as well. So guys, let's go do that. Was it chapter 10? Okay, so guys, let's solve number 61 together. Because now you have the foundational understandings to solve this. So guys, oh, that's interesting. That's interesting, guys. Check this out. I mean, you see number 61, right, on page 419? But then look down 3 inches and to the right, and that's where the subsection on partial pressures starts. They actually put this question in the wrong section because you can't solve this question without partial pressures. But we're going to solve it together. So guys, hey, how are you? Thank you. She didn't look happy. Did I offend her? I don't think so. Really? That's a first for me. So guys, number 61 reads like this. We're going to do this together. So number 61 says hydrogen gas is produced when zinc reacts with acid. It actually doesn't have to be sulfuric acid. You may remember that from last year in lab where you put little pieces of zinc and hydrochloric acid, collected the hydrogen gas, stuck the burning wood splint in, it popped and you giggled. Remember that? Same thing. Different gas. This is sulfuric rather than hydrochloric acid. It just creates a different salt. But we still get hydrogen gas. So then it goes on to say if 159 milliliters of wet H2 is collected at 24 degrees Celsius and a barometric pressure of this, how many grams of zinc have been consumed? Now, guys, in order to address this question, you've got to understand this idea of wet hydrogen. So, in order to help you understand this, let's take this back to the lab that we did last year. And you guys know what kind of artist I am, but you've learned to be patient. So the idea was that we had a test tube rack. I know. And then guys, in that test tube rack, you had a test tube, and in the bottom of that test tube, you had some surprisingly concentrated hydrochloric acid. We should probably make this true to the question. It's sulfuric, right? Does it even give us the molarity? It really shouldn't matter because it's not the limiting reactant. Okay, so guys, we've got some H2SO4 in here, and you of course know that because this is aqueous, that means the sulfuric acid is dissolved in water. And then what you did is you added probably several chunks of zinc to this, and as you did that, this thing began to bubble pretty vigorously. And so then you placed a larger test tube over the top of the smaller test tube, and because hydrogen gas is less dense than air, the hydrogen gas rose and it filled the test tube. And then at some point, you then removed that larger test tube from your source of hydrogen gas, you shoved in the wood splint, and it popped. Is it all coming back to you? Okay, here's the thing that we need to talk about now. Last year, you had the idea that that test tube was full of hydrogen. And it was, but not all the way. So guys, here's what happened. As this hydrogen gas rose, initially this test tube was full of air, right? So as the hydrogen rises to the top of the test tube. It displaces the nitrogen gas, the air, which is largely nitrogen. It displaces the nitrogen gas, and very quickly this becomes a test tube simply full of hydrogen. But it turns out that's not the only gas inside the test tube. What else is in there? Interestingly, the answer is water vapor. Guys, the reason is because, and by the way, I'll draw you another picture in a minute. The reason is because while the hydrogen gas is being evolved, and you see the bubbles like crazy, you actually also have the water that the sulfuric acid is in evaporating. Water evaporates. And when that water evaporates, it follows the hydrogen because water vapor is less dense than air. The water vapor actually rises, and it also fills the test tube. Now, the question is, so what? Well, guys, you may remember last year, do you remember this lab? Remember that guy? This was one of the last labs that we did last year. And what you did was you took a Bic lighter, remember, and we pulled all the workings off the top and we stuck a little piece of brake tubing on it. We're going to be doing that next week. Guys, what you did is you actually took a Bic lighter and a graduated cylinder. And you filled the graduated cylinder with water, and then you took the Bic lighter, you weighed it before, and then you weighed it after the experiment, and you actually displaced this butane gas into the graduated cylinder, and by doing that, you were able to figure out the value for R. Do you remember doing that? Vaguely? Okay, so guys, let's talk about it. In order to solve this, what we were solving for is R. So in order to do this, let's talk about where we got the rest of our numbers. So how did we get the temperature of the gas? Do you remember? Same as the temperature of the water because the gas bubbled through the water. Where did we find the number of moles of gas? It was the mass difference converted to moles. Do you remember that? Okay. Then guys, how did we find the volume of the gas? It was just right off the graduated cylinder. Now, here's the tricky bit, and actually you're probably going to feel a little deceived, because guys, last year you did this wrong. So let's talk about how you did it wrong last year. Let's talk about how we could fix it this year, and then let's go back to question number 61. Guys, how did you find the pressure of the gas? Do you remember? Yeah, so and let's talk, guys, one of the things that you had to do was make sure that the water level inside the test tube was the same as the water level in the trough. Guys, given what you now understand, do you understand how that's kind of like the idea behind a manometer? That if this level is not the same as this level, what do you know about their pressures? They're not the same. So guys, what is causing the pressure inside the tube? The butane. Guys, what is causing the pressure outside the tube? The atmosphere. And if it looks like this, what is greater, the pressure of the atmosphere or the pressure of the butane? The atmosphere. So what you've got to do, and Daniel, this was back to your point, what you've got to do is move the cylinder down so that the two levels line up with each other. Now we know the pressures are equal. But Daniel, to your point, functionally what that does is it decreases the volume of the gas a little bit, because when you push this down, it increases the pressure and makes it a little bit smaller. So, guys, let's then draw this correctly. So, now we'll say that we have made our adjustment so that the water levels are equal, okay? Now what do we know about the pressure inside and outside the tube? They're the same. So say that atmospheric pressure is 1.0. Let me maybe change this. Let's do this. Say that the pressure outside the tube, let's just make it standard pressure. Let's say it's 760 torr. What is the pressure of the butane? It is not 760 torr. Even though the water levels are the same, it is not 760. Why not? It's not greater than. Why is the pressure of the butane not 760?
Oh, because of water vapor.
That's not the only thing inside the tube. Guys, the total pressure inside the tube is 760. But that pressure is not only being created by the butane, because there is also some water vapor in there. So the total pressure is 760. And that's what we actually used as the pressure of butane last year. But now, guys, let's talk about what the pressure actually is. So, in order to find the pressure of the butane, if we know atmospheric pressure, what do we have to know to find the pressure of the butane? The pressure of the water vapor. Grab your books and open up to page 1058. So guys, let's say that our water is at 25 degrees Celsius. We're going to say that our water is at 25 degrees Celsius. It's a little warm, but we'll go with it. So guys, if our water is at 25 degrees Celsius, what else is at 25 degrees Celsius? The gas. And why does that matter? Because that tells us the pressure of the vapor over the water. So guys, find 25 degrees Celsius, and you find out that at 25 degrees Celsius, the vapor pressure of the water above the water vapor above the water liquid is 23.76 torr. So guys, the pressure of the water is 23.8 torr. So what is the pressure then of the butane? 760 minus 23.8. You get the idea? So guys, that is what it means to be collecting wet gases. Because if you're collecting a wet gas, you then have to attribute for the pressure of the water vapor mixed up inside the gas that you're trying to isolate. And guys, frankly, until you get deep into your college chemistry experiences, guys, this is really the gold standard for collecting gases. The reason is because you can isolate the gas from other contaminants very easily, because initially your tube's just full of water. And if it's full of water, it's not full of other gases. And then you can limit the number of gases that contaminate this, because if it was in fact initially full of water, the only gas that you could have in there is the gas you're trying to study and water vapor, and we can deal with that. So, when you're collecting gases, typically they will be collected over water or by water displacement. And if that's the case, you've got to account for the water vapor. So, what does this have to do with Dalton's law of partial pressures? Well, pressure total is equal to PA plus PB. Our pressure total is 760 torr. Our pressure A will be our butane. Our pressure B will be our water. We look up the pressure of water from our table on page 1058. That was 23, this is really a mess, 760, and solve that for X. And that's how we come up with this. And that's where Dalton's law of partial pressures comes in. Oh, I don't care. No, yeah. I think I'm okay. No, that's 24. What are you? Oh, are you talking about question 61? Oh, yeah, no, this was, okay, so let's go back and look at question 61. Yeah, so guys, here's what we're going to do. Let's go back to question 61, and now I'll bet we can think our way through this. Because they tell us that the total pressure is 738, and then is this at 24 Celsius, I guess? So at 24 Celsius, the partial pressure of the water is 22.38 torr. Subtracting and watching significant digits, we now, or actually decimal places, we now know that the pressure of that hydrogen gas is 716 torr, which we'll then need to convert to atmospheres by dividing by 760. And this will then allow us to calculate number of moles, because the pressure is 716 converted to atmospheres, divided by 760. The volume was given in milliliters, convert to liters. We're solving for moles. R is a constant. It gave us the temperature. Just solve for the number of moles. And then, guys, moles of hydrogen relative to moles of zinc is actually a 1-to-1 ratio, because the question says how much zinc did you react? And so this tells us the moles of hydrogen. Dimensional analysis allows us to convert to moles of zinc. But again, the only way that you could have solved this is by understanding Dalton's law of partial pressures, and specifically how that applies to collecting wet gases. You good? You okay? Okay, so guys, with that said, we've got one more thing to do to wrap up what we're up to today. So there is another problem. We're not going to solve this, but it's you'll notice how it says, a sample of gases collected over water. Same idea, just a different problem. I just made this one up, so we're not going to do it. Okay, so now guys, to wrap up the day, we are going to talk about, oh, wow. That is one sticky note. Dang. I can fix it. I'm like Bob the Builder. Have you guys seen the Saturday Night Live sketch right after the economy collapsed in 2008, 2007? Where they're suggesting what we should do about the collapse of the economy, and their solution is fix it. That's it. That's just their solution. Fix it. This guy's like, this is a simple 3-step process. Step 1, fix. Step 2, it. Step 3, fix it. And anyway, it went on and on and on for weeks, and it got really funny. So, YouTube that tonight. Go look up Saturday Night Live Fix It sketch. There's days of it. It's wonderful. Okay, so guys, what we're going to do now, and actually, you know what? I want to take you back. Going back to slide number 2, we talked about this idea of proportionality. And let's dwell there for a minute. So guys, this idea of proportionality tells us that if we know the relative number of moles of gas in a mixture, we also then know the relative pressure of those gases in the mixture. Again, we had this neat little experience with the big red pen where we canceled these things out by factoring them out, and we understand that because the pressures, or I'm sorry, the temperatures R and volume are the same, they factor out, and we see then that there's a ratio, there's a relationship, a proportionality between the number of moles and pressure. And we extended that idea by hopping over here. I know this is review, but we extended that idea by hopping over here and talking about the idea that there was twice as much blue moles, so it's twice the pressure in whatever units we choose. You okay? Okay, so guys, with that idea, what we're going to do then is we are going to extend that and talk about an idea called mole fractions. So guys, this is literally fractions of moles. It's a ratio, a proportion. So the idea is this, and you may want to write these foundational thoughts down. Because each gas in a behavior behaves independently. You're thinking about me living on the outskirts of Rawlins, Wyoming, the neighbor in the binoculars. There's so much space inside these gases, guys, that they behave independently. Because this is true, we can create a relationship, a proportion. We've already said this. We can create a proportion between the amount, moles, and the pressure of those components in a mixture of gases. I tell you what, though, there was no cooler place to grow up than the outskirts of Rawlins, Wyoming. We'd get on our motorcycles at like 9 in the morning and wouldn't be home till dark. Just gone. It was such a cool way to grow up. And then I got to high school and all of my friends became alcoholics, and then it wasn't quite as neat, but... To which part? Because San Jose, California is so much like Rawlins, Wyoming.
Well, I mean the high school with the alcohol.
Did Matt just call you guys alcoholics? Oh, okay. Okay. All right. I had to clarify. Okay, so guys, so we are now talking about relationships. And as we talk about relationships, we're going to talk about fractions or ratios. So guys, we're going to write the fraction like this. Don't write this part down. So we're going to solve PivNert again for Pa, which gives us NERTVA. But I'm writing it on one line. The reason is because it then allows me to represent this. We are going to talk about ratios of pressure and ratios of moles. We've already done this. Twice as many blue as red. Pressure of blue is twice that of red. But guys, do write this down. This is the idea. Write this down. So we are going to talk about the ratio of the pressure of some component A compared to the total pressure of the gas. So guys, fix that in your brains. You got it? So just PA over P total. So guys, this is what we're saying. Going back here, you're okay. Going back here. So let's mix these together. Like so. So now we've mixed them together and we're familiar with what we've got. So let's talk about a pressure ratio and let's talk about a number of moles, a particle ratio. So actually, you know what? I want to flip those around. Let's write it out. So let's talk about particles and let's talk about pressure. So guys, let's talk about the red gas. Ready? How many red particles are there? 5. How many total particles are there? 15, right? So 1/3 of this gas is red particles. Now, what is the pressure of the red gas? What did we say? 1. What is the total pressure? Get it? they're the same. Guys, the particle ratio of a component compared to the overall sample, and again, those would be in moles and not numbers of particles, is equal to the pressure ratio. So, with that idea in the background, we're now going to yippee skip over here, and we're going to take this relationship and we are going to represent it like this. So we've got a pressure ratio. Pressure A, we'll call those the red guys. Pressure total, and then pressure total, the whole pressure of the mixture. But guys, we've established this. Pa is equal to nRTVA, right? So now let's get out our big fat canceling pen. And now it's not even a factoring pen. It now is in fact a canceling pen. And guys, all of these cancel out because they're the same. R is the same, temperature is the same, volume is the same. I find it much more satisfying to using the big canceling pen, but I actually digitized it too. Not quite as satisfying, but you get the idea. But now guys, look at what happens. When we remove the stuff that we canceled, we now have just NA divided by N total. But isn't that the relationship that we looked at a second ago, a third and a third? But now look at what we can do. Guys, we give this a name. So let's take this equation, and I'm going to focus on it. Got it? And guys, this is actually equal to what we call a mole fraction X. Don't write that down, but do write this down. Guys, this is equal to a mole, just trust me, it's equal to a mole fraction X. So what is a mole fraction? Read it, but don't worry about it because you'll see it mathematically. This is a dimensionless number. What does that mean? No units. What is it though? Well guys, it is simply a ratio of moles of one component compared to total number of moles. So it's this. Get the idea? So it's simply that. So here's what we can do. Let's set this equal to X. So this is X. And X, which is the mole fraction, is the number of moles of a component divided by total number of moles. But now guys, check this out. Because this is equal to X, can we say that? Uh-huh. And now look at what we're going to do. We're going to solve this for PA. That's what you want to write down. So P sub A is equal to X sub A times PT. Why did I not have you write any of that down? It's all on the AP sheet. Do you see it there? So guys, you'll notice that they give us the equation. It's the second one down. P sub A is equal to pressure total times X sub A. And they even give you what X sub A is. It's moles of A divided by moles total. But guys, all this is a mathematical representation. It is a mathematical representation of this. This idea that if a third of something is particles, then a pressure of it is also a third. That's all it is a mathematical representation of that. So, what can we do with this? Well, we can solve problems like this. Don't try to write it down, but we're going to solve it. This is actually real data. It says, from Voyager 1, scientists have determined that the composition of the atmosphere of Titan, which is Saturn's largest moon, is this. So the total pressure at the surface of the moon is that. Is that above or below standard atmospheric pressure here? Almost twice. Then it goes on to say if we took a 5 mole sample of this atmosphere, and they actually did this, they found that around 4 of those 5 moles is nitrogen, 0.6 of those moles is argon, and then 0.3 of those moles is CH4. What is the partial pressures of these gases? So guys, let's solve it for one, and if you can solve it for one, you can solve it for all. So we go like this. We go pressure of component A is equal to pressure total times X sub A. So guys, let's make our A nitrogen. Let's do this for nitrogen first. So we want to know the pressure of nitrogen. But that is equal to the pressure total, which is 1,220 torr, times the mole fraction. Well, guys, as it says on your AP equation sheet, the mole fraction is moles of N2 divided by total moles. Well, it tells us moles of N2, 4.10 moles, and the total moles is 5. And that's it. So, guys, basically what this means is about 82%, 4.1 divided by 5, about 82% of that gas by moles is nitrogen. So guess what percentage of its pressure is from the nitrogen? Also 82%. So all we've got to do is take 1,220, multiply that by 4.1, divide that by 5, and 82% of 1220 being really liberal with significant digits, it's about 1,000 torr. Then you could go back and do that for the other two samples. And then if you really want to see this idea become full circle, if you took those three pressures and added them up, what would you get? 1220, because they all add up to the total pressure. You guys okay?
Yeah.
All right, so guys, we got some homework to do. Looks surprisingly like this.